Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series. In this one, we talk about confidence intervals about a population variance. Okay, let's get to it. We've done a couple of videos already about confidence intervals. We've done one about a population proportion and about a population mean. Now, this one is going to be different because those were based on this underlying principle that the distributions of the sample proportion and the sample mean were normal. They're normally distributed. But the variance is different. See, the issue is the variance has this square in it. And so then it can't possibly be normally distributed and be even because it can't be negative. Here's an example. I have the distribution here of the SAT scores from our children of immigrants. I'll put that link to that data set in the description. You can see here, fairly symmetric, not perfect, but fairly symmetric. Whereas if you look at the sample variance, I took 10,000 samples of size 30, you can see here that the variance is skewed right. Pretty smooth distribution, but it's skewed right. Again, because of the squared, it can't be negative. So we're going to need a new statistic. Now, if we look at a variable that's normally distributed with a mean, mu, and a standard deviation sigma, we can create a new statistic called a chi-squared statistic. It's another Greek letter chi. It's spelled usually when you see it written in English, it'll be C-H-I, but it's not chi like the T, it's chi. It's a chi-squared, and it's n-1 times the sample variance squared divided by the population variance squared. And this is the chi-squared distribution. It has n-1 degrees of freedom. Now, this is kind of a new concept here, this degrees of freedom. We're not going to get into the heavy theoretical idea about what degrees of freedom are, but the basic idea is suppose you have 3 children and 3 lollipops. Well, the first has 3 choices. So there's degree of freedom for her. The second only has 2 choices. And then the last one doesn't have any choice. There's no degree of freedom there. And so if we had 3 people and 3 lollipops, then there's only 2 degrees of freedom. So it's 1 less than the size in the sample. And that's the kind of waving your hands idea behind degrees of freedom. All right, let's talk about this chi-squared distribution. It's not symmetric, as we said, it's always skewed right because it can't be 0. If we want to have alpha area in the tail, so alpha over 2 in each, then we can have these critical values, chi-squared alpha over 2 on the right, that's alpha over 2 area to the right, and then chi-squared 1 minus alpha over 2 over on the left. It's a little confusing, but remember the subscript means area to the right. That means then that we should have 1 minus alpha of them between chi-squared 1 minus alpha over 2 and chi-squared alpha over 2. Again, this should be 1 minus alpha, where alpha is like 0.01, so 99% would be between these two. Now, chi-squared is that n minus 1 times s squared over sigma squared. So let's do some algebra with this compound inequality. If we take reciprocals of everything, you might remember this from algebra. When you take reciprocals of an inequality, you have to change the direction of the inequality. And now let's reverse the order. And so I'll kind of read it backwards. Let's clear fractions. Let's multiply everything by n minus 1 s squared. And then we have this new inequality that 1 minus alpha of them, in this case, 1 minus alpha of the variances should be between n minus 1 s squared over chi squared alpha over 2 and n minus 1 s squared over chi squared 1 minus alpha over 2. So this is a 1 minus alpha 100% confidence interval for the population variance. There are some strict criteria here. This was assuming that the population was normally distributed. So the population must be normally distributed in order for you to do this confidence interval. Second is, if you're looking for a confidence interval for sigma, the standard deviation, you just take the square root of each of those 3 parts. Like usual, let's finish with an example. And I was wondering here, what's something interesting we could look at in this database? And we have this SAT scores, and I wondered, is there a difference in the distribution in SAT scores versus those whose fathers are not citizens and those whose fathers are citizens? You can see here that they look pretty similar. The means are almost identical, so that isn't any different, but it looks to me maybe like the first distribution is a little more condensed than the second one. I don't know, it's hard to tell visually from the histogram. So let's see if we can do a confidence interval for the standard deviation and compare those whose fathers are citizens versus those whose fathers are not citizens. Now this confidence interval is under stat variance stats. So we're only going to get a confidence interval for variance this way. One sample with data, and we're going to do the SAT score, and we're going to group by the father citizen. When we hit compute, you can see the results here. Now, this is really, really important. You'll notice these are for the variance. It even says it, one sample variance. The sigma squared is the variance here of math, and then these are the sample variances. So these confidence intervals here, these confidence intervals are for the variance. We need to manually go in, take the square root of all of them, and then we round to one more than the data. These were SAT scores. They're rounded to whole numbers, so we'll round to the 10th place. These now are the two confidence intervals for the standard deviation of SAT total score based on whether the father was a citizen or not. If we kind of visualize those, for the non-citizen fathers, we have 44.4 to 49.5 for the standard deviation. And then for ones whose fathers were citizens, 46.1 to 49.0. So really, they're pretty similar. They overlap, so we certainly can't say that they are different at all. In fact, if you look at the histograms and kind of overlap them, you can see that they basically have the same shape, same center, pretty much the same spread. And that pretty much reinforces what we saw between the confidence intervals. There was no statistical difference between those standard deviations. All right, that's it for this video. I hope this was helpful. If you're interested in seeing more of these, you can subscribe, hit the bell to get notified. As always, thank you to the Elgin Community College Board of Trustees for approving my sabbatical during the spring 2021 semester, and that's what gave me the time to record, edit, and produce all of these videos and share them with you. So thank you so much for watching, and I'll see you in the next one.